Hi student, I am H.M. Kulkarni from MG Art Science Commerce College Malegaon. Today we are going to discuss last chapter of 11th Science. The name of chapter is Semiconductor Devices. In this topic, first topic is Introduction of Semiconductor Devices. In this modern life is heavily dependent on many electrical gadgets. It could be a cell phone, a smartwatch, a computer, or even an LED lamp or tube light. They all have one common factor semiconductor devices that make them work. Semiconductors have made our life very comfortable and easy. Semiconductors are materials whose electrical properties can be tailored to suit our requirements. Before the discovery of semiconductors, electrical properties of materials could be of two types conductors and insulators. Conductors, such as metals, have high electric conductivity. For example, conductivity of silver is 6.25 to 10 raised to 7, whereas insulator or bad conductor like glass has very low electrical conductivity. Electrical conductivity of silicon or semiconductor, for example, or it lies in between conductors and insulator. Temperature dependent of electrical conductivity of semiconductor can also be controlled. The following table gives electric conductivity of some materials which are commonly used. Electrical conduction in solids. Electrical conduction in a solid takes place by transport of charge carriers. It depends on its temperature, the number of charge carriers, how easily these carriers can move inside a solid, its crystal structure, types of the nature of different defects present in a solid etc. There can be three types of electrical conductors. It could be a good conductor, a semiconductor, or a bad conductor. First, conductor. The best example of conductor is any metal. They have large number of electrons available for electrical conduction. These electrons are called free electrons. Metals are good conductors of electricity due to the large number of free electrons present in them. Second, insulator. Glass, wood, rubber are some common example of insulators. They have very less number of free electrons. Third, semiconductors. Silicon, germanium, gallium arsenide, gallium nitride, cadmium sulfide are some of the commonly used semiconductors. The electrical conductivity of semiconductor is between the conductivity of metal and the insulator. The above graphs or figure shows the temperature dependence of electrical conductivity of a typical metal and semiconductor. When the temperature of semiconductor is increased, its electrical conductivity also increases. The electrical conductivity of metal decreases with increase in its temperature. Variation of electrical conductivity of semiconductors with the change in its temperature is very useful property and finds application in a large number of electronic devices. Classification of semiconductors. A. Elemental semiconductors. Examples are silicon and germanium. Compound semiconductors, cadmium sulfide, zinc sulfide, etc. Organic semiconductors, anthracis, doped phthalocyanins, polyanions, etc. Elemental semiconductors are compound semiconductors are widely used in electronic industries. Discovery of organic semiconductors is relatively new and they find lesser application. The conduction mechanism in a semiconductor can be better understood with the help of band theory of solids. Band theory of solids, a brief introduction. We begin with the way electron energies in an isolated atoms are distributed. An isolated atom has nucleus at the center, which is surrounded by number of revolving electrons. These electrons are arranged in different and discrete energy levels. When a solid is formed, a large number of atoms are packed in it. The outermost electron energy level in a solid are occupied by electrons from all atoms in a solid. Sharing of the outermost energy level and resulting formation of energy bands can be easily understood by considering formation of solid sodium. Any energy level can accommodate only two electrons, one with spin up state and the other with spin down state. For sodium atom, the topmost occupied energy level is 3s level. This level is called valence level. Corresponding energy band is called the valence band. Thus, the valence band in solid sodium is the topmost occupied energy band. The valence band is half filled in sodium. Figure shows the energy bands in a sodium. You can see the figure. When sufficient energy is provided to electrons from the valence band, they are raised to higher levels. The immediately next energy level that electron from valence band can occupy is called conduction level. The band formed by conduction level is called conduction band. In sodium, valence and conduction bands overlap. In a semiconductor or insulator, there is a gap between bottom of conduction band and the top of valence band. This is called energy gap or band gap. Figure 14.4 shows. Above figure shows the conduction band, the energy gap and the valence band for a typical solid which is not good conductor. It is important to remember that this structure is related to the energy of electrons in a solid and it does not represent the physical structure of a solid in any way. The difference in electrical conductivities of various solids can be explained on the basis of band structure of solids. Band structure in metal, semiconductor and insulator is different. The following figure shows the schematic representation of band structure of metal, semiconductor and insulator. For metals, the valence band and the conduction band overlap and there is no band gap as shown in figure 14.5a. Electrons therefore find it easy to gain electrical energy when some external field is applied. They are therefore easily available for conduction. In case of semiconductors, the band gap is fairly small, of the order of 1 electron volt or less than, which is shown in figure 14.5b. When excited, electrons gain energy and occupy energy levels in conduction band easily and can take part in electric conduction. Third diagram. Insulators, on the contrary, have a wide gap between valence band and conduction band as shown in figure 14.5c. Diamond, for example, has a band gap of about 5 eV. In an insulator, therefore, electrons find it very difficult to gain sufficient energy and occupy energy levels in the conduction band. Thank you.